It's been called the quiet workhorse of space science, a means of transporting ambitious and hefty scientific experiments to the edge of space.
We're going to start inflation at this time. Everybody got earplugs that wants them?
While the technology may seem old-fashioned, it remains the quickest and most cost-efficient avenue to near space.
When you compare to satellite missions that take 5 to 7 years to develop and millions of dollars, scientific ballooning can be done on a fraction of that budget and in a fraction of that time.
From the study of the atmosphere to the origins of the universe, it's been the vehicle for some of the most significant scientific discoveries of our time. And the future holds even more promise for one of the greatest scientific stories never told. No one launches more scientific balloons from more places around the world than NASA's Columbia Scientific Balloon Facility, based in Palestine, Texas.
The strength of the program is that we can fly very heavy payloads, up to 8,000 pounds, and very large payloads. We can put those experiments into near space above 99.5% of the Earth's atmosphere.
The scientific balloons they use are made of an incredibly thin polyethylene film, only 0.02 centimeters thick, the thickness of an ordinary sandwich bag. They can fly that 8,000-pound payload, the weight of 3 small cars, nearly 23 miles high to an invisible ceiling where the atmosphere ends and space begins, and can stay there riding upper atmospheric winds for up to 6 weeks. Due to the natural difference in density between the helium gas used to fill the balloons and the air, as these zero-pressure balloons ascend in the atmosphere, they expand to volumes of up to 40 million cubic feet, nearly the size of a stadium like the Louisiana Superdome.
But to launch those into space would take a very expensive launch vehicle. I mean, really, literally on $100 million for the launch. And whether we do these for, certainly 1/100th of that or less.
And we can have greater access to space, more frequent flights of science, and in the end, the scientist gets their payload back.
From New Mexico to Arctic Sweden and Australia to the coldest and driest continent, Antarctica, the Columbia Scientific Balloon Facility launches 15 to 20 balloons a year over 4 to 5 campaigns.
All right, guys, we're ready.
Locations are typically dictated by science or longer data gathering air time.
Any science that can be done above about 99.5% of the Earth's atmosphere, either looking up or looking down, can be done on balloons.
The scientists using scientific balloons include some of the world's most seasoned researchers and university professors, even graduate students.
The young scientists can design the experiment, build the experiment, fly the experiment, and analyze the data, go through all aspects of a space mission, which is not possible with our large space mission.
And ballooning is a vehicle for world-class science. In the mid-1980s, an ozone hole was discovered over the Antarctic continent. The initial measurements were all made from scientific balloons. Another high-profile balloon-borne experiment called Boomerang in 1998 showed the geometry of the universe is basically flat and continually expanding, a finding consistent with the Big Bang Theory. And in 2003, a cosmic ray experiment called CREAM orbited the South Pole 3 times, setting a long-duration scientific balloon record of 42 days at float.
15 years ago, this capability would have been unheard of, and we got quite a bit of attention in the science community from people who are interested in these extended duration flights.
Getting beyond the atmosphere by balloon involves handing complete responsibility for the scientific payload and launch to the Columbia Scientific Balloon Facility crew.
So I'll be communicating with you all the time during that.
While there are subtle rigging differences from launch to launch based on specific scientific needs, whether launching from Sweden or here in Fort Sumner, New Mexico, the main layout of a typical scientific balloon flight train is essentially identical. This hands-on rigging remains one of the most complex and critically important processes.
We'll set a show time, we'll come out, we'll hang the gun, then we'll go out to the launch pad.
It begins with the pickup of a scientific payload with a specially designed launch vehicle.
And attached to the payload will be suspension cables that will go upward to what we call a truck plate. That truck plate is actually holding the entire flight system to the launch vehicle. From that truck plate, there will be a suspension ladder that will go over the launch vehicle, and that will connect down to the parachute separator unit.
Rotators should be on.
This unit separates the parachute from the payload to prevent a wind-filled parachute from dragging and damaging the payload after termination. The nylon parachutes range in size from 46 feet to 159 feet in diameter for the largest payloads.
And then we'll have the terminate fitting, which is the link between the parachute and the balloon. That terminate fitting will have an explosive device on it that we'll initiate to bring the balloon down at the conclusion of the flight. And then connected to the terminate fitting will be the balloon itself. And on top of the balloon will be helium valves that will open at the end of the flight as a secondary measure to terminate the balloon.
Before a payload is declared flight ready, it undergoes a dress rehearsal of sorts, called a compatibility check.
The line of sight data isn't coming in yet either.
That's an exercise where the payload is taken out and typically hung from the launch vehicle, and the instrument is fired up in its entirety. All of the functions are tested, and when the scientist determines that CSBF gear is not interfering with what he's trying to do and vice versa, then the payload is declared flight ready.
Here, telemetry, the ability to send and receive data and control functions to and from the payload, is tested and confirmed.
There's two types of telemetry. One is used on relatively short flights that might last anywhere between 6 and 48 hours. That's called line of sight telemetry.
Line of sight typically gives the scientists the first initial couple hours of float data that they can thereby look at and see how their instrument's performing.
For longer duration, over-the-horizon flights, satellite-based telemetry is used. Of the two, line-of-sight bandwidth is considerably greater.
We can actually go up to about 1 megabit per second and have multiple 1 megabit streams coming down from the payload.
Enough bandwidth to allow scientists to completely reprogram a payload, in extreme cases, during the first hours of flight.
Just put one up at 1,000. That way we kind of get an idea of what the wind speed is and what kind of direction that we're looking at.
The Columbia Scientific Balloon Facility crew uses small tethered pilot balloons to gauge local winds. Surface winds for a launch cannot exceed 6 to 7 miles per hour in the first 200 vertical feet. From 200 to 1,000 feet, the height of a balloon when released, winds must be less than 12 miles an hour.
It's about 14 knots. Yep.
And from top to bottom, winds must be in a constant direction. Any shift in variation or speed during inflation can shred a balloon, a dangerous order for crew and scientists.
Depending on where you are in the world, coming up with that combination of weather can be very difficult, and sometimes there can be delays in launches of a week or 10 days or perhaps as long as 2 weeks.
So that east direction is probably our best bet?
Yeah, 68 degrees, 70 at the top of the balloon, still 70 degrees.
And this is for what time?
That's 18Z, 8 p.m.
Despite an optimistic weather forecast, this launch day initially looked like a no-go.
Well, we're just waiting now for this cloud mass to go away. And when it goes away from us enough, we should be able to establish a solid direction. Look, we got good low-level wind conditions, 3-4 knots, great. So now if we can just get some of this precip to be out, we can launch. I think we might do it today.
With the Columbia Scientific Balloon Facility crew on standby, CSBF meteorologists closely monitor weather conditions to identify a favorable and time-specific launch window.
All right, guys, we're ready.
Stand by. Release the balloon.
That zone is really just all instinct after that. Once the balloon comes out of the spool, you're just operating on instinct, at least I am.
Going to the right just a little bit more.
And you're watching the flight train as it comes up over the launch vehicle. You're maneuvering the vehicle, talking to the driver, telling them which way to go.
Let it go all the way up.
The 15, 20 seconds or so that it takes to launch one, it seems like a short time, and it is a short time, but in that 15, 20 seconds, your mind it's got a lot going through it.
All right, stop. Good job, guys.
No, I don't ever get tired of participating or watching a launch. It is quite unique, and it's an experience that we just really, really cherish a lot.
In roughly 2 hours of float time, balloon and payload will arrive at the edge of space. Riding westerly upper atmospheric winds, this sub-millimeter telescope called BLAST will gather precious data for a full week before being returned to Earth.
The balloon at float can be seen well in excess of 100 miles. We've had reports from airline pilots that they could see our balloon and were trying to report near misses to the FAA when the balloon is 125, 145 miles away. From the ground, you can probably see it well in excess of 100 miles.
What's it look like tomorrow?
Campaign Director Bill Stepp oversees the monitoring, termination, and post-flight recovery of scientific payloads and balloons.
We have a requirement to keep a chase aircraft essentially within 1 hour of flying time from the balloon at any time.
What we have is...
While Stepp and his team monitor the westward tracking balloon in real time with sophisticated software.
The safe distance standoff distances are 5 miles in radius around the projected landing
point of the payload, and we make sure that there are no populated areas within that area.
A set of statistics is run that tells us what the probabilities are of actually injuring someone on the ground. And those numbers, the probabilities have to be extremely low, like on the order of 1 in a million, before we're allowed to bring one of these systems down.
At the predetermined conclusion of the flight, the aircrew is called in for termination.
They will fly to the location of the balloon, start communications with the FAA, and start getting clearance from the FAA to terminate the flight or separate the payload and the balloon.
After a visual inspection of the projected landing point, a telemetry command is sent, firing an explosive squib that separates parachute and balloon at 120,000 feet in the air. This separation also creates a tear in the balloon, releasing the gas.
The payload descends on the parachute over a period typically of about 50 minutes.
The aircraft will stay in station right around the payload and monitor the descent of the balloon and the descent of the payload.
Once the payload is on the ground, there's a set of sensors that we fly that can tell that it's on the ground, and at that time a set of explosives is fired that separates the parachute from the payload to keep it from dragging in case there's strong winds in the impact area. We have the capability of predicting where a parachute will go from 120,000 feet, typically within 2 to 3 miles. We can tell where it's going to hit the ground within 2 to 3 miles. In over 2,200 scientific balloon flights, we have never even significantly injured a member of the launch crew during the launch process, and there has never been a single public injury associated with any phase of a balloon launch or flight or termination and impact. That's a pretty significant success rate, and we're very proud of that. Safety is taken very seriously within the balloon program.
In the end, the payload is recovered and returned to the science team to fly another day. Scientific ballooning, the best kept secret in space science.
We're not blasting into the air with beating the air to death with propellers or screaming through the air with rocket engines or jet engines. Nothing could be more elegant or simple. It's a continuity. I don't think lighter than air travel will ever be obsolete just because it is so perfectly elegant in its application.
In this age of the space shuttle, the International Space Station, and rocketry, scientific ballooning is still relevant and plays an important role in science because it provides for lifting very heavy payloads to very high altitudes and for a fraction of the cost of flying on the space shuttle or the International Space Station, do world-class science.
It's a quiet little engine that always has. And we've been going along providing very economical platforms for scientists since the late 40s. And I really believe that it's the little engine that always will, too.
Good job, guys.